Okay, so piecewise functions are also real popular when you're dealing with limits. And so I wanted to just go over a few things about piecewise functions. Piecewise functions are functions like, take a look at these, like 1, 2, or 3, where you have different rules for various parts of the coordinate plane. So like on number 2, you have one rule used when x is less than 1, and a different rule used when x is bigger than 13, and yet another one when you're between 8 and 13. So they can be very interesting. Okay? They can have lots of different pieces. Sometimes the ends of the pieces overlap. Sometimes there's jumps horizontally. Sometimes there's jumps vertically. And all of that affects what happens when you look at the limit on these. So I just wanted to go through some examples. I'm going to try to do this pretty quickly because I want to get it posted and I'm tired. Okay, so on the first one, we're just evaluating. Oops, I got to snip it. Let me see if I can. Okay, so we're just evaluating the function. So we're asked to find g of 5. So what you do is you have to see, well, which rule applies when we have an input of 5 or an x of 5. So you have this bottom rule you use when x is -6, and then you use the top rule for everything else. And so that means I need to take and plug in the 5 everywhere there is an x on that top rule and just work it out. So it'd be 25 minus 6, which is 19, over 5 plus 6, which is 11. So g of 5 would equal 19/11. Okay. All right, so let's just keep going from there. So next, I'm doing the same thing, f of 8. So 8 and x of 8 would fall in this range because you're allowed to be 8. So you use that rule, and then 8 times 8 turns out to equal 64. So the answer to 2 should be 64. All right, now on 3, it says look for the domain and the range. You're being asked for the domain and range of the function now. Okay. All right, so I'm kind of looking at this. Let me blow this up a little bit. All right, this is really the different sections of the domain, but since we have a graph, we can look at that. Do you see how here we have these points? Then it picks up here and keeps going. Then it picks up here. So if we're doing domain, we want to smash all of those points to the x-axis. So it would go from way over here at -5. Okay. It would go to -2, but then you would use a different rule, but it would still be defined at -2. And it would go all the way to 4. You wouldn't use that rule for 4, but you would pick up right here and it would be defined, and then it would go all the way to 14. So it turns out to be defined all the way from -5 to 14. That's your domain. Okay. Now for range, you really need to see the graph. Very hard to do these without a picture sometimes. So the lowest possible point is right there at 0. And it gets as high as 4, but the 4 is not included. The 0 appears to be included. So the range should be from 0 to 4, and there were no missing pieces in there. Like, even though this had this vertical jump here, this made up for it over on this side. And even though there's a vertical jump there, it was defined here. Okay, so that's why it turns out the way it did. Okay, let's go ahead and look at these two because they're in this snip, and then we'll come back and do the other one. So here it works well to think, okay, x equals 0 is where I'm going to break my graph. All right, when I'm to the right of the graph, I'm going to graph y equal 5. When I'm to the left of I said the graph, when I'm to the right of the y-axis, I'm going to graph y equal 5. When I'm to the left, I'm going to be graphing this. Okay. And so y equal 5 is a horizontal line up there at 5. And I use that when I'm at 0, so I'm going to put a closed dot on that end. Okay. Then here, what I know is I should have a v. And it turns out that the v would have happened right there at 5, like your absolute value would have just moved up to be right there at 5. Okay, so what you can do on this is you're using that when you're to the left of the x-axis. So when you're to the left of the x-axis, you could maybe just plot a couple points. If you put in a -2, that would be 2 plus 5, which would be at 7. So it'd be up here. When you put in a 0, you'd be at 5. So it's going to do that. And it's not included at that end, but it does overlap with the other one that's there. And then if you wondered where the V happened, the other side of the V would be over here. We just don't use it because we're only supposed to use that when we're to the left of 0. Okay, let's look at number 6. Okay, it has 2 when I'm to the right of 1. So here's where the coordinate plane is going to be broken. That's not a vertical asymptote. That's just me organizing my thinking. So I'm going to have y equal 2 to the right and y equals -1 minus x when I'm to the left of 1. So y equal 2 is a horizontal line at 2, and I use it when I'm right there at 1. Then this is a line that has a slope of -1 and a b value of -1. Okay, so b value of -1 and a slope that's -1. So that means if I go up 1, I have to go to the left. If I go down 1, I go to the right. So it's going to do something like that. And then it's not included here, but it is included there. So see how you have that vertical jump? See how the limit approaching 1 would be one thing from the left and a different thing from the right? The limit right there at 1 wouldn't exist, would it? Okay. It's a kind of function you deal with a lot with limits. All right, let me go ahead and pull this down so we can look at 4 and 7 on this page. Can we snip that? Okay. All right, so when I'm to the left of 1, so here's 1. Again, that's not an asymptote. That's just me separating my graph. One side I have y equal x. This side I have y equals 1 over x minus 1. You know, feel free to find some ordered pairs. That might be the easiest way. If you put in x of 1, y would be 1. X of 2, y would be 2. So 1, 1, 2, 2, 3, 3. This is going to be a line that does that. And I use it to figure out what happens at 1. So that's a closed dot there. Okay, now this is a rational function. So if you didn't know much about that, it could be tricky. There would be, if I were graphing just that, there would be an asymptote at 1. Okay, and then it would have a horizontal asymptote at the x-axis. Okay, if I put in a 0 for x, it would cross right here. So this is going to do something like that. Okay, and then the other piece of it would have been over here, but you're not supposed to use it, right? Because you're only supposed to use it when you're to the left of 1. So that's going to look something like that. Okay, so you're going to have the left part of the rational function and then just from there on up. And this little line I drew is not part of your graph. It's just me trying to organize and figure out where to split the coordinate plane. Okay. And so I'm going to have one rule being used to the left of -1, one being used between 1 and -1, and then one to the right of 1. Those aren't asymptotes. I'm going to emphasize that. So to the left, I'm going to do that. To the right, I'm going to do that. And in the middle, I have y equal 2. So y equal 2 in the middle. I'll go ahead and get that one out of the way. And notice it's an open circle on both ends of that. So let me do that. Okay. All right, then to the right, I'm going to have y equals 2x plus 1. You might just put in a 1, and you see the y would be 3. So that would be about right there. I got that being too big. You can't really see. So here's y equal 2, open circle on either end. And then 1, 3. And then 2 would go to 5. Which would be about right there. And I would have a line that does something like that. Okay. And it would have a closed dot on the left side of that. Right, then to the left over here, I have y equals 2x squared, which is, I know is a parabola, just a little more narrow than a typical one. And so I'd like to know what happens at -1 itself. So I'm going to plug that in. It's 2 times 1 is 2. So -1 at 2. So it's going to, let me do this one in blue. Kind of wish I'd used a different color on the other. So it's going to fill in that little dot right there. Okay. And then I need to see some others. So if I put in a -2 and square it, I would get +4 times 2. -2 is way up here at 8. And then -3 would be 9 times 2. -3 would be way up there at like 18. So it's a parabola, but you just have it rising pretty rapidly like that. Okay, and then all those 3 pieces go together to create your piecewise function. All right, so we're almost done with that. Okay, let's go ahead and go to the next page. Just had 3 more in here where we're going kind of backwards this time. Okay. So here I've given you the piecewise function. I'm just asking you to think about what the graph could be. All right, so you got 2 pieces. So your piecewise function is going to be like f of x equals, and then you're going to have these 2 pieces. One of them is used when you're to the right of 1, including the 1. One of them is used when you're to the left of 1, less than 1, okay? When you're to the right of 1, you've got that horizontal line. That would be y equal 3, wouldn't it? So this should be 3. And you use it when x is bigger than or equal to 1. This right here is x equals -5. So you'd put a -5 right there. I shouldn't have said x, that's a y. Y equal -5. So I'd put a -5 in there. Okay, and that's that part. And then domain, the endpoint of this piece is right below the endpoint to that piece, and that one's filled in. This one is open. So if you smashed all these points to the x-axis, everything would be covered up. So for domain, it would be negative to positive infinity, be all reals. Okay. When you do range, you actually only have 2 possible values. Not the interval between -5 and 3, but the range would be just the set consisting of -5 and 3. No other numbers, just those 2 values. So discrete spots. All right, let's look at number 9. With number 9, okay, on number 9, I see this hole right here. And I see this being redefined. So one of the things you might do initially is just think of it like this. Think of it like a line. And if you wanted to, try to figure out the equation for that line. So it looks like it has a y-intercept of -3. Then you could count to find your slope. Maybe go all the way to there. So that would be 1, 2, 3, 4, 5, 6, up 6, and then over 1, 2, 3. So the equation looks like, for that line, looks like it would be y equals 2x plus 3. And that would be defined as long as x was not 3. Okay. And then when x does equal 3, you define it to be down there at -2. Okay. All right, so when you look at this one, the domain is actually going to be all reals because that fills in for that missing spot. Okay, the range is actually, so the domain would be all reals. There's no gap horizontally because this fills in that spot if you smashed everything to the x-axis. But if you thought about the range and you smashed all these over, you'd have this coming to here with an open circle, and then all of that would be defined. So there's an opening, a missing spot at 3. So -infinity to 3, then keep going from 3 on. Okay. All right, now, let me double check something. I said it had a y-intercept of -3, and I just noticed I put +3, so that would have been a -3. All right, everything else looks okay. Right, and then it really turns out that this might actually be even more elaborate than that. It might be a 2x minus 3 with a factor of x minus 3 on top, and then an x minus 3 on the bottom. That would produce this exact picture as well. The x minus 3's would cancel, giving you a line, but the x minus 3's would produce that hole. So really, it's more like this. Okay. All right, now, number 10 is just a word problem dealing with postal rates. Okay. We did a problem with postal rates and then went on and did the limits. So this should look a little familiar to you. All right, so on this one, we've got, it's 25 cents to mail a package weighing 1 ounce or less, 25 cents. So that would be right there. Okay. And then 20 cents more for each additional ounce or fraction thereof. So when I go to like 1.1, I have to jump up 20 more cents. So I'd be at 45. So it'd be like that. And then if I go past the 2, okay, I'd have to jump up 20 more cents, which would be at 65. Okay. And then jump up 20 more cents and be at 85. So something like that is the idea. And then let's get the endpoints correctly. All right. So when it is 1 ounce, it does cost you 25 cents. So you do use that. But then if you go just slightly to the right of that, you're going to have to pay more. So we're going to do an open circle on the left, but then at 2 ounces, you'd be paying 45 cents. So the pattern would look like this. Okay. And this was the problem where if you considered the limit at, say, 1, you considered the limit of L of x as x approaches 1 does not exist because the left and the right-sided limits aren't equal to one another. But if you did the limit as x approaches 1.5, okay, then it would equal, what is that, 25 and 20? That would equal 45 cents. So we dealt with postal rates in one of the problems we did. All right, so there we finally got it done.